All right, today we're going to talk about the conservation of mass, which you also sometimes hear called the conservation of matter. Either one that you call it is fine. And the conservation of matter just says that you're not going to destroy matter, you're not going to create matter during a chemical reaction. Sometimes it can appear that, oh, look, I made something that was not there before, or I destroyed the atoms. You may make a new substance that wasn't present before, but all of the reactants, every atom that was there in the reactants is going to equal all of the atoms and all of the mass that was there in the products. And so because of that, because you're not destroying matter, the law of conservation of mass says you're not making atoms, you're not destroying them, you are going to have the same number and the same kind of atoms at the beginning that you do at the end of a chemical reaction. It's just going to be that those atoms have broken apart and regrouped to make that new substance. So for the conservation of mass, your reactant, so reactant 1 plus reactant 2, is going to have a mass that's also equal to the mass of your products. So the total mass of a substance does not change during the chemical reaction. If you mass it before, it should equal the mass after. So in this example, calcium oxide combined with carbon dioxide is going to give you and produce calcium carbonate. So when you start out, calcium oxide is CaO plus CO2 yields CaCO3. So here you can see you have one calcium atom in your reactant, you have one calcium atom in your product. You have 1, 2, 3 oxygen atoms in your reactants, and you have 3 oxygen atoms in your products. You have 1 carbon in your reactant and 1 carbon in your products. So you can see all of the atoms that you start with are present at the end. They've just broken apart and regrouped to make this new substance, calcium carbonate. Since all those atoms are going to be there before and after, your before equals your after, then the mass of the before is also going to equal the mass of the after. That's what the conservation of mass means. It means you're conserving the mass. You're not making anything new. You're not destroying any of the atoms. You're simply changing the arrangement of them to make a different substance. So here, our mass of our calcium oxide was 56.08. and the carbon dioxide was 44 grams. So that means that the mass of our calcium carbonate is going to be 100.8 because your mass before is always going to equal your mass after. Now, when we're talking about the conservation of mass, we're going to talk about two kinds of systems. An open system is a system where the matter during the chemical reaction can escape into the surroundings. So in these instances, these are the ones that students say, hey, look, I destroyed the atoms. You didn't destroy the atoms. They just escaped into the surroundings. An example of an open system is wood burning in a fireplace. When that chemical reaction is happening, you're not capturing the atoms that are given off in the gases, the smoke, into the atmosphere. So that system is open. The matter can escape into the surroundings. If you want to be able to show the conservation of mass, you have to use a closed system. And a closed system is where it's completely closed. There's no way that the matter can go out. There's no way that new matter can come in from the atmosphere. And so an example of a closed system is a chemical reaction happening inside a sealed Ziploc bag, or here in this picture they're doing it in a sealed flask. They're dumping it together here, and they're showing you that the mass before is equal to the mass after. Now, because of this idea of conservation of mass, that we're not making atoms, we're not destroying atoms, or simply during a chemical reaction breaking them apart and the molecules or the atoms regroup into different molecules, because of that, when you write out a chemical equation, your chemical equation has to be balanced. And that just means that if it's balanced, it's even. It's like on a scale that we showed the picture earlier. You have the same number of reactants, same number of atoms and kind of atoms before as you do after. Your before equals your after. Your reactants equal your products. So here is an example of a balanced chemical equation. It's not the actual chemical formulas, it's showing you it in a picture format, but you can see here you have 1, 2, 3, 4 of the red atoms before, and you have 1, 2, 3, 4 of the atoms after. 2 of the blue before and 2 after. So this is a balanced equation. The second one here is not balanced because if you put it on the scale, it wouldn't be even. It would be lopsided because your before doesn't equal your after. And conservation of mass says your before has to equal your after, both with the number of kinds and types of atoms, and then that therefore is going to have your mass equal your before and your after. So here we have 2 of the red atoms before and 2 after, so that's equal. But we have 2 of the blue before and only 1 after, so that is not balanced. All right, here's a couple of examples that actually have the chemical formulas and the chemical equation written out. So let's see if we can tell if these are balanced or not. Let me get my pen out here. Okay, so here we have before. I'm just going to put a B here for the before. And then after. All right, so we have 2 iron before. And we have 2 iron after, Fe. Okay, before we have, let's see, we have 2 Cl, Cl2, but we have that 3 times because we have a coefficient. So that means for Cl, we have 6 atoms of chlorine. And here we have Cl3, so that's 3 atoms of chlorine, but we have that twice, so we have Cl 6 times. So this one is a balanced equation. This one, we have 2 LiCls. So we have 2 lithiums for our before, and we have 1 lithium for after. Before we have 2 Cls because we have LiCl twice, so we're going to have 2 Cls there, 2 chlorine atoms, and then we have Cl2, which is 2 chlorine atoms. So this chemical equation is not balanced. It doesn't have the before equaling the after. So this is going to be an unbalanced equation. All right, now we're going to do a little bit of practice with conservation of mass and balanced and unbalanced equations.